From Utah Public Radio, this is UnDisciplined. I'm Matthew LeBlanc. Earlier this year, as I was working on the 300th episode of this program, I reached out to chat with our show's first producer, Alyssa Roberts. And one of the things we laughed about was that back when she started, Alyssa really didn't think much about science.
Mostly I just love podcasts, and I was like, yeah, let's try it. Let's see where it goes. And then it was really interesting. Like I learned so much. I think about the show all the time. And I think it's cool that there's this platform because, like I said, I never thought that I would think that any of this stuff was interesting. But then when they're in front of you talking about, like, yeah, I had to go walk into an active volcano, you're like, oh, cool, this science stuff. Like, maybe I should look into this a little bit more.
The person that Alyssa was talking about right there, the scientist who walked into a volcano, that's Karen Lloyd. Karen actually joined us twice in the early days of this program, first in 2018 to talk about microbial dark matter, and then again in 2019 to discuss the relationship between microbes, carbon, and the deep earth. But it's been a few years since we checked in. And in that time, Karen has been really busy. After 12 years at the University of Tennessee, where she was a professor of microbiology, she moved across the country to accept a role as professor of earth sciences at the University of Southern California. She's authored or co-authored nearly 100 new articles since we last chatted, including papers describing major discoveries on carbon trapped in marine sediments, the evolution of the archaea domain of life, the role of microbes in processing methane in the environment, and how bacteria cycle sulfur on the bottom of the ocean. And somewhere in between all of those things, and being a mother and an avid runner and an advisor to lots and lots of graduate students, Lloyd wrote a book. It's called Intraterrestrials, Discovering the Strangest Life on Earth. The story is her first-hand account of the hunt for life beneath the Earth's surface and how new discoveries are challenging our most basic assumptions about the spectrum of life on this planet. It's also a celebration of fieldwork and teamwork, and an introduction to some hypotheses on the origin of life itself. Karen Lloyd, welcome back.
Thanks for having me. It's really fun to be back here.
I want to revisit the volcano story because we got part of it when we chatted with you in the early days on this program. But back then, we were packing two scientists into every show, and there's this story that you tell in the book that we didn't hear back then, and it is so amazing. You're in the Poas volcano in Costa Rica. You and Katie Pratt from the University of Rhode Island and Steve Turner, who has lots of experience descending into these things, says he won't be joining you.
Yeah.
Why does he tell you this?
Because he wants to minimize his exposure to risk, and he doesn't really need to go that day. And I was like, what? What am I doing?
And if that's not enough, then Martin DeMoore, another very experienced volcanologist, tells you something about your shoes.
Yeah, he was like, just make sure you keep your boots moving so they don't melt while you're in the volcano.
But don't move them too fast, because if you move them too fast, then you're going to slip into the volcano.
Yeah, because we were standing on this like really steep slope of gravel. Like, you know how gravel doesn't really hold you very well if it's a steep slope. And at the end of that steep slope was a big pool of volcanic water that I had just measured the pH of, which was 0.85.
Which is bad.
It's battery acid.
Which is, you don't want to fall in that.
Yeah, your skin falls off. So yeah, it was a pretty nerve-wracking moment.
And if that's not all enough, then your field guide, Carlos Ramirez, tells you something about what to do if there's an emergency.
Yeah, he said, so I mean, this is not embellishment. I literally was like, I hadn't thought about what would happen if this thing erupted. So I asked him in the moment, I was like, what's our escape route? And he's like, oh yeah, that's awesome. I'm so glad you asked. You turn around and you enjoy it because that's it for you. So just enjoy your last moments. I was like, what?
But you still did it. You still did it.
It was, so the nice thing about Poas is that it gets angry and then it calms down, and it gets angry and it calms down. And so it's periods of sort of phreatic eruptions where it's sort of popping off all over the place. tend to be a little bit gradual, and it had been very quiet and not steaming for a long time. So we had a pretty good guess that it was going to be good that day. We were not playing fast and loose.
Not for nothing, though. 56 days later, this thing erupted.
Yeah, and it's actually erupting right now too. All my WhatsApp is blowing up with videos that my friends from Costa Rica are sending me.
Oh my gosh! And some of these videos, when they take them, because the cameras are down in the volcano, when the thing erupts, you get sort of like a few last photos, and then that's it, right?
And then that's it.
Yeah, yeah. Now, this wasn't the first time you braved some risk to gather samples that, with some luck, would lead to microbial discoveries. And the book starts with a story about your first dive to the bottom of the ocean in a part of a submersible that, I'm not kidding, is called the coffin.
It's a colloquial term. I don't think it's official, but we do call it the coffin.
Because it's little tiny.
Yeah, because it's coffin shaped, and also in the first iteration of the submarine, two men asphyxiated. Actually, we're not quite sure if it was from lack of buildup of CO2 or if it was from the cold exposure, but that was a pretty sad event, and it was actually one of the sub's designers' son was one of the men who died, and so it's been completely redesigned, and we have a lot more safety precautions now.
But it's not okay. We have safety precautions, but you keep doing these things. You've done these things across your career. But I mean, the point I'm making is not to like build you up as this like really heroic, brave person, which I think you are, but also that like the data is worth it. The effort is worth it. The science is worth it.
Yeah, because we can't just study things in the abstract. It's great to grow cultures in laboratory, and laboratories are lovely places because you can control all the variables. And Francis Bacon taught us that you change one variable at a time and do the test, and then you do it a bunch of times, and then you change another variable. But nature doesn't function like that. Nature has an infinite number of variables that are interacting with each other and changing it an infinite number of ways. And so if you really want to study reality, you have to get out in it.
And because of all of these variables, and we're going to get into some of this, but because of all of that, and here's the thing, we've only just scratched the surface of what life is. Microbial life, intraterrestrials, as you and some other people have come to calling the things that live miles below the terrestrial Earth and even miles below the surface of the ocean, have evolved in all of these ways that are really, really hard for us to understand unless we go down there and we collect them.
You have to study them in nature. It's kind of like if you wanted to study lions and you just went to the zoo. You'd be like, okay, lions naturally eat little round pieces of meat that has been prepared for them. And you would totally miss the hunt that takes down like a zebra on the savannah.
Okay, I'm going to build on this analogy a little bit here, right? Like, what if everywhere we looked, we found lions? Like, we didn't even know, like, lions actually exist in New York City, not in the zoo, right? But just like they're out there, they're in the dark, right?
That would be so dangerous. Some kind of apocalypse movie. Animal
I think it would be
apocalypse.
great. And they were like dark matter lions. We couldn't really see them, but they were there. But this is the world of microbial life. Intraterrestrials are everywhere we've looked. You write, we have not yet encountered a depth at which life does not exist. How deep are we talking?
Well, it has to stop at some point. I mean, life as we know it cannot survive the temperatures and pressures of most of the mantle, for instance, and definitely not the core. So it has to stop at some point. But sort of that almost represents more our inability to get samples than it does anything else, just because the deepest parts that we've gone into in the crust are there because of mining, of commercial mining. And so the deepest samples that we have are from diamond mines and gold mines. I mean, there's a lot of cracks in the earth. If you're tiny, inside the crust is a great place to live.
And these things, you use the word live. What we're talking about here is clearly life, but it's structured differently. You write that life is perfectly possible in places like these, as long as you are not too attached to multicellularity or oxygen, which are two things that, by the way, I'm very attached to.
I know, me too. I use them every day.
But tell me, okay, tell me about that. Like, how do organisms? I understand. I think our audience understands how organisms can be singularly cellular. But let's talk about how organisms breathe without oxygen? What do they breathe if they're not breathing oxygen?
Yeah, a lot of what we think of as being necessary for life is really just details. It's not the essential fundamentals of life. To understand that, you have to go to basic thermodynamics. So that just means like the movement of heat and energy. And that's all that life does. We all do it, but we have to dissipate energy. We have to take two chemicals or light energy and convert it into something else and capture the energy from that. And that's what life has to do. And you can do that with a lot of different chemicals. Oxygen is the one that we use because it's so oxidized. We get a ton of power from that reaction. But that's not the only possibility. You can basically look across most of the periodic table, and most of the things on there can be breathed by something somewhere.
This is where we get into things like chemolithoaudiotrophy, right? Sustaining life through chemical energy rather than solar energy. There's some cool creatures down there that do this.
Yes, there's many different kinds, and they have many different ways of collecting this carbon dioxide. So, up at the surface, plants convert carbon dioxide into biomass, and we eat the biomass, and we eat animals that eat that biomass. But in the subsurface, there's no light, and so they just get the same. They basically do the same process, but with chemical energy.
When we recognize that life can exist in all of these different ways. And by the way, one of the things that you write in this book is sort of like when you think about the ways that life can exist and then you look in those places where it can exist, lo and behold, there's life existing in that way. But when you think about it in those ways, the calculations for how much life exists go pretty crazy.
Yeah. It's you can do a lot with all these variety of chemical reactions, and you can also leave Earth too. I mean, this is one reason why I think it's entirely probable that we have life on other planets because these same chemical gradients exist on Europa. And it would just be crazy to me that life wouldn't find a way to catalyze it.
One of the problems here on Earth for discovery of microbial life, and this is one of the many things that we talked about a few years back, is that intraterrestrial microorganisms don't grow the same way in petri dishes that terrestrial microbes do. You can't just like put them in a little dish and wait for them to grow. So we use DNA to hunt for these little guys.
Yeah, so we use DNA to hunt for them, and actually, there've in the past couple of years, we've had a couple of breakthroughs where some folks, Hiroyuki Amachi's lab in Japan and Krista Schlepper's lab in Austria, have both managed to get some of these non-growing, never going to grow on a petri dish, deep branching groups to actually grow in their laboratories, which is, I think, one of the greatest breakthroughs in our field in the past 20 years.
And are they just discovering things left and right?
Oh my gosh, it just blew the lid off of everything. Having these things, I talk a lot about how important it is to go in the field, but I never want to knock the laboratory. Like we learn things in a laboratory. So the fact that they've been able to get these things to grow has really expanded our understanding of what these things actually are. And it's been incredible. One thing that they have discovered is that they are crazy slow. And that is something that you can't get around. They just double every maybe 2 weeks or something, which if you grow E. coli on a lab bench, it's gonna double every, like, half hour or so.
Which is what makes E. coli disgusting and terrifying.
Yeah, disgusting, terrifying, and incredibly useful, like, all of those things.
So I want to dive into this slow part because it does fundamentally change in another way, in a temporal way, what is possible for life. And you write about this in the book too.
Yeah. It has taken me years of basically, like, cogitating on this in the background of my brain while doing other things to fully, like, understand well, not that I fully understand it, but just to wrap my brain around something that lives that long. It's hard to even see how much of a framework death in 100 years is to everything we talk about with biology.
Yeah, like long-lived things are things that live more than 100 years, short-lived things are things that live a couple of days. But then there are these microbial parts of the spectrum of life out there that are very likely growing very slowly, pausing for a long time, and then growing some more, literally waiting for tectonic shifts to trigger whatever it is deep and small inside of them that tells them to grow again. And the result are organisms that are perhaps thousands, tens of thousands, maybe millions of years old.
Yeah, we can't discount it. It sounds crazy, but that is a very rational conclusion from all of the data that we've seen.
You have a great word for these guys.
Eonophiles.
It's so good. It's such a good word for them.
Yeah, it took us a while. I talked to a lot of Latin scholars and Greek microbiologist colleagues of mine and microbiologists all around the world. And that was the one word, we tried a bunch of different prefixes, and that was the only one that everyone agreed actually made sense.
Can I tell you how much I love the fact that when you decided to do this, you went and talked to Latin and Greek scholars and like really worked at this instead of what, quite frankly, most of us would do, which is just like find two words and, push them together in a portmanteau that may or may not work, but who cares because it sounds cool. And you still came up with a word that sounds cool.
Yeah, I think it sounds cool too. It's kind of the British spelling. We want to say aeonophiles in the American version, but it would be eonophiles. I think that this is something that is important enough to have spent a little bit of time on, because once you start putting a word out there, it'll get picked up and used. And what if I picked a real dumb word? So I wanted to pick the right word.
You could have called it like a Lloydophile. I mean, have you ever tempted?
That would be terrible.
Is there anything out there that's named after you yet?
No, I don't think anything's named. I'm not a culturer person. So.
Okay, here's the reason I ask. And the reason I ask is because one of the things that I learned in your book is that there are so many discoveries that, in fact, it sort of becomes sort of like old news. Like, oh, we just found thousands of more microorganisms, and like they're just numbers right now. They're scraps of DNA. There could be a little Lloyd out there.
Yeah, maybe someday. One can hope.
But these discoveries are now to the point where there are so many of them that, again, this stretches out the imagination of what life is because it is just so expansive. So many new microorganisms are discovered each year that have all figured out how to survive in tremendously different ways. That it's really stretching out this idea of what is possible in life to the point that a lot of biologists for a while there were pretty displeased with the microbial takeover of the tree of life because all of a sudden our part of the tree of life was getting, comparatively smaller and smaller. And you wrote that you understood in a way because it's hard to look at two little dots under the microscope and believe that they have less in common with each other, and these are your words, than a mushroom and a baboon, or a tree and a shark, or a slime mold and my uncles, all of whom are eukaryotes.
Yeah, I have amazing uncles. They're wonderful. They're way better than slime molds.
But not way different than slime molds.
No, they're pretty much the same thing. I mean, they all just appeared like a few million years ago.
And this has sort of like a lot to do with that time thing that we were talking about earlier, because your uncles and the slime mold and the trees and the sharks and the baboons and the mushrooms, they've had millions of years to differentiate from one another. That seems like a long time. But these little guys are microorganisms on this earth have been separating from each other for a very, very long time.
Billions of years. It's so much more time in which to evolve new traits that it's hard to, you say the word billion, million, they sound kind of similar. Like they're not similar. That's a lot more time, and you can do a lot more things. Like figure out how to breathe solid iron, for instance.
Because of this, at one point you make a little mistake in your notes. You wrote about humans and other plants.
I literally wrote that. Like, I can't believe I have so many degrees in science, and I'm just like, I can't believe I wrote humans and other plants because I was comparing them to the great diversity of life that's out there, and humans and plants are kind of on the same branch.
Right. I mean, it's incorrect taxonomically, but it's not so very incorrect in the grand scheme of things. We're very close to plants, much closer to plants than many, many single-celled organisms are to one another.
Exactly. I made that mistake because that's my frame of reference because I work on this stuff every day.
When that is your frame of reference, does it cause you to wonder if we even have a good handle on what life is?
Absolutely. If we missed things that are this deep on the tree of life and that are this weird for, the 10 million years that humans have been on this planet, like what else are we missing? It's going to be something.
How do you turn that off? How do you turn that off, like, when you're walking down the street?
But why turn it off? It's fun. It's a great way to live.
What's next for you? What's the next discovery that you're after? Because you're still, I mean, your career seems like it's like you've packed a lot into a short amount of time. You still got a long way to go, right? Before you're on a golf course somewhere or whatever.
Yeah. One thing that really keeps it fresh and keeps it going is my students. I just always have this cadre of undergraduates and PhD students and post baccalaureates and postdocs. And those people, each one of them is just beginning. They're just starting out. And so all the different projects that I have, like sort of in my larger portfolio, are led by one of those people. And so it's kind of amazing just to kind of sit back and be like, well, what are you doing? What are you finding? And to facilitate them making that discovery. Because I just know how influential that was for me. And it's really rewarding to see them doing it.
One of the things that your students are scratching at, that fellow researchers are scratching at, and that you're interested also in, is how our evolving understanding of what is possible when it comes to this thing called life shifts our understanding of what is possible in terms of how life began. You have some interesting theories on this as well.
Yeah, it's probably the most half-baked part of the book. I included it just because I don't think that this framework is one that we talk about a lot, and I just wanted to throw it out there, and it could be a dead end. We'll see. But, this dependence on thermodynamics really leads us to thinking about the second law of thermodynamics, that entropy must always be created. And entropy can be a hard thing to understand. It could be understood as disorder. Sometimes it is, but disorder is not always entropy. It's more better understood as like the quality of energy, like how useful is this energy? And so we're constantly dissipating energy in ways that make it sort of less useful, throwing out heat, for instance. And if you look at life from that perspective, then it's really about process, thermodynamics, like moving. And none of this gets me to a nice pat. We came from this pool at this date, catalyzing these chemical reactions. Like, that's not where I'm headed with this. It's more just drawing on sort of the early thinkers, Lotka and Vernadsky, and sort of some of their ideas that process had to be just as important as function. That doesn't really end us up in like this is how life formed, but I think that there's something helpful about thinking about it as thermodynamics rather than like what did it look like? Was it round?
When you think about these sorts of things, this goes back to the opening story of your book, right? You were down at the bottom of the ocean, where these vents are, that some other scientists, many other scientists have hypothesized were the likely place where life began. And, that's a possibility, but there are so many other possibilities.
Absolutely. If all you need is a really good gradient, a chemical changing over space or time in a way that allows life to get set up, and then you can sort of imagine these processes leading on processes. And life as a process is all about creating opportunities for entropy, making new situations where entropy can be created in ways that are more productive and more complex than you would if you just had an abiotic process. Like if you think about methane and oxygen, we use methane as natural gas to heat our houses. And so you can light a match and burn the methane and make it all go away. But if you put a methanotroph, if you put a bacterium that eats the methane into that system, you'll end up with a lot of biomass and interesting forms and some new types of enzymes that are maybe helpful for society. And so there's a lot more possibilities that are created by life. So you can see life as a possibility creator if you think about it like that, I think it might help our discussions of the origin of life.
That's Karen Lloyd. Her new book, Intraterrestrials, is a firsthand account of the hunt for life beneath Earth's surface and how new discoveries are challenging our most basic assumptions about the spectrum of life on this planet. Karen Lloyd, thank you.
Thank you for having me. This is super fun.
UnDisciplined is a production of Utah Public Radio, and if you happen to live in Utah, you can listen to us on UPR every Thursday morning at 10:30. If you miss us then, you can listen to every episode of UnDisciplined wherever you get your podcasts. Our program is supported by the College of Humanities and Social Sciences at Utah State University. And from listeners like you, you can support our work at donate.nprstations.org/UPR. Our producer is Reagan Edelman. Our theme music is Little Idea by Benjamin Tissot. And I'm Matthew LaPlante. Thanks for listening. Now go have big ideas.